Hi, today we're going to be looking at the response of an RL circuit when our input signal is one sine wave of a particular frequency. So, our circuit looks like this. We have our sinusoidal input and our two elements. Our resistor is 1 kilo ohm and our inductor is 1 millihenry. So the first thing we need to note about this circuit is that our omega equals 650 radians per second. So radians per second. And that our input voltage we can represent in a phasor form like we did with the RC circuit. So it's going to be 5 with 0 degrees angle because there's no phase in this sine wave. Then we want to substitute our elements by their corresponding impedances. So we know that the impedance of my resistance is 1 kilo ohm. And we know that the impedance of our inductor is L times, J omega L. J omega L. So in this case, our impedance will be 650 J ohms. Yeah. So we can put that here. 650 J ohms. So now we proceed to treat our circuit like any other normal circuit, in which case we can also apply the laws that we know, Ohm's law, Kirchhoff's law, and analyze the circuit. In this case, I will solve it by using a voltage divider. If we're interested in the output voltage here, at the inductor, then we will just do a voltage divider, input voltage times this impedance over the sum of both impedances. So our output voltage is our input voltage times the impedance where we want to calculate our voltage over the sum of both impedances, which is 1K plus 650 J ohms. So now we would like to convert this impedance, which is the series of the two impedances above, into phasor form so that we can do these algebraic operations. So our output voltage will be, then I just put my V in here, which is 5 at 0 degrees, times 650 ohms. We need the magnitude of that. The magnitude of an imaginary number is just the imaginary part. And the phase of an imaginary number is again the inverse tangent of the imaginary over the real. In this case, it's going to be 90 degrees because our real part is 0. So I have the inverse tangent of infinity, of plus infinity. So I have 90 degrees there. And here, I'm going to have the magnitude. So my magnitude would be 1K squared plus 650 squared, square root of that. And again, my angle, the angle of this, it's going to be the inverse tangent of my imaginary part, which is plus 650 over 1K. And that will give us, so V0 will be 5 at 0 degrees times 650 at 90 degrees. So these are volts and these are ohms over 1.2 at 33 degrees kilo ohms. So now we proceed to calculate this multiplication, this product, and this division. And how we do that is as follows. The product of two complex numbers in phasor form like this is the product of their magnitudes plus, and the phase is the sum of their phases. So my complex number will have the magnitude, which is 5 times 650 as magnitude, which gives me yeah, 3.25 K with an angle of 90 degrees. So 5 times 650 gives me 3.25 K at 90 degrees. And then over this so I'm going to put here, K, the K. 1.2 at 33 degrees, also kilo ohms. So this kilo ohm cancels out with this kilo ohm here, and the volts here. And now we have two complex numbers and we need to divide them. So the division of complex numbers, the magnitude will be the division of the two magnitudes, and the phase is the difference of the two phases here. So that our output voltage will be, now I lost it, 2.72, which is 3.25 over 1.2, with an angle of 90 degrees minus 33 degrees is 57 degrees volts. So this is our voltage. And remembering that in such a circuit, the frequency of the sine wave of all the components is the same, is omega, then we get a response that will be shown in the screen now. So that would be how our input voltage looks in comparison with our output voltage measured at the inductor. So this is how we calculate circuits when we have inductors like that and an input sine wave where we know the frequency, and it's only just the one frequency. So in the following videos, we will be looking at the frequency response of this circuit when we have many, many frequencies and not just that one. Thanks for watching.